Welcome to the Deep Dive. Today we're really getting into Think Python, Second Edition by Alan B. Downey.
That's right. And the book's core idea is teaching you how to think like a computer scientist.
Exactly. So our mission here is to unpack the key ideas, the main techniques from the book, pulling out the important stuff to help you understand the fundamentals of programming and computation. And we're sticking strictly to what's in this book.
And that frame, thinking like a computer scientist, it's really central. The book describes it as this mix of approaches.
A mix. How so?
Well, like the precision you find in math, the design thinking from engineering, and the way natural scientists observe things. It's about using these formal languages very clearly, building big things from small parts, and figuring out how systems work just by watching them.
Okay, so if we're learning to think that way, using this book as our guide, where do we even begin? What's step one in the Python world, according to Downey?
It starts right at the beginning with the tool that runs the code, the Python interpreter. That's the program that reads your Python code and actually executes it. The book shows two main ways you interact with it.
Right, you got the interactive mode. That's where you type something, hit enter, and bam, you get a response right away.
Yeah.
Like a command prompt or a scratch pad.
Exactly. It's great for, quick tests, trying things out, and then there's script mode.
That's for longer stuff.
Yeah, you put your commands, your whole sequence, into a file that's your script, and then you tell the interpreter to run the entire file top to bottom.
And the first thing everyone does.
Tradition, it's almost always hello world using the print function.
Yeah.
It's like the initiation, right?
The classic. Okay, so interpreter running, printing, hello world. What's the most basic kind of stuff that programs actually work with?
Values. They're the fundamental pieces of data. Could be a number, could be some text. And importantly, every single value has a type.
And the type tells you what kind of thing it is.
Exactly. What kind of data, and crucially, what you can do with it.
The book introduces a few core types right at the start.
Yep. Integers whole numbers, like 2 or 42. Python calls that type int.
Okay.
Then floating point numbers, numbers with a decimal point, like 3.14159, that's float. And text, which are sequences of characters called strings, the type is str.
And there's a way to ask Python what type something is, right?
The type function, super useful. You just give it a value, like type 2, and it tells you class int. Or type hello gives class str.
This feels like where one of those really subtle but critical points comes in, the difference between the number 42 and the string 42.
Oh, absolutely. This hits on that precision of formal languages straight away. 42 is an integer value. It's a quantity. Python knows you can do math with it.
But 42?
That's a string. It's just two characters, a 4 followed by a 2. It looks like the number, but to the computer, it's just text. You can't say, multiply the string 42 by 3 and expect to get 126. Type 42 confirms it's dr.
That really highlights the difference the book talks about between formal languages like Python and natural languages like English.
Yeah, it's a great comparison. Natural languages are, well, messy but flexible. Ambiguity is everywhere. Words mean different things. There's tons of redundancy. You can often understand someone even if they mumble or miss words.
And idioms, metaphors. Break a leg doesn't mean,
Exactly. Context is everything for us. But formal languages, they're built for computers.
Designed to be precise.
Totally unambiguous, less redundant, and strictly literal. Every symbol, every comma, every colon has one specific meaning, and the interpreter follows that meaning to the letter.
Which is why, as the book points out, the details matter so much. A tiny spelling mistake, a forgotten punctuation mark.
Things you wouldn't even notice in an email. But in Python, it can stop the whole thing cold. The interpreter can't guess what you meant. It just sees the structure is wrong, a syntax error, and it stops.
No guessing allowed. It just follows the rules.
Precisely.
Okay, so we have values, we know their types. How do we start using them in programs that do more than one thing? We need variables, I assume.
Yes, variables are basically names that you make refer to values. The book suggests thinking of them less like boxes holding values and more like labels you attach to values.
And you attach them with an assignment statement.
Right, like message hello. You use the equal sign to assign the string value hello to the name message. Now message refers to that string.
And you mentioned statements. Are they different from expressions?
They are. A statement is an instruction that Python executes. It does something, performs an action like assignment. It doesn't produce a value itself. An expression, though, is a combination of values, variables, operators that Python evaluates down to a single result value.
So 1 plus 1 is an expression.
Yep, evaluates to 2. If n refers to 17, then n plus 5 is an expression that evaluates to 22.
And if you have lots of operators in an expression, there's an order.
Standard math order, yeah. PEMDAS is the usual way to remember it. Parentheses first, then exponentiation, like for powers, then multiplication and division, evaluated left to right, and finally addition and subtraction, also left to right.
The book highlights one operator that might be new for some folks, but seems really useful. The modulus operator, percent.
Oh, yes, the remainder operator. It's surprisingly handy. Minutes per sixty gives you the leftover minutes after taking out the full hours.
Oh, neat.
Yeah, great for checking divisibility, like number per su equals 0, 0, tells you if number is even, or getting the last digit of a number with number percent 10, lots of uses.
And amidst all this precise, literal code, we need a way to leave notes for humans, right? Comments.
Crucial. Anything on a line after the hash symbol, hashtag, is just ignored by Python.
Yeah.
And the book makes a good point. Good comments explain why the code is doing something, not just what it's doing. Often, what should be clear from well-written code itself, the why gives context.
Okay, so we write our precise code, add helpful comments,
Yeah.
but things still go wrong. The book is clear, errors happen, debugging.
It's just part of the process. Everyone makes mistakes, bugs. Finding and fixing them debugging is a core skill. The book helpfully categorizes the kinds of errors you'll encounter.
What's the first type? The ones Python catches right away.
Syntax errors. These are problems with the actual grammar or structure of your code. You forgot a colon, misspelled while, used an invalid symbol. The interpreter finds these when it first tries to read your code before anything even runs.
Then there are errors that pop up while the program is running.
Runtime errors, also called exceptions. The syntax was okay, the program started, but then something impossible happened during execution.
They're like dividing by 0.
Classic example. Or trying to access index 10 in a list that only has 5 items. When that happens, the program usually crashes and Python prints a traceback.
A traceback thing looks scary, but it's actually helpful.
Very helpful. It shows exactly where the error occurred, the line number, the function, and the sequence of function calls that led up to that point. It's Python saying, whoa, I was doing this, then bam, right here, something went wrong and I had to stop.
And a third kind, the sneakiest ones.
Semantic errors. Oh, these are the tough ones. The code is perfectly valid. Python, it runs without crashing, but it just doesn't do what you intended it to do.
So the logic is wrong somewhere.
Exactly. You told the computer to do something, and it did it faithfully, but what you told it was flawed. Maybe you calculated tax wrong or sorted in reverse order. Python can't tell you there's a semantic error because, as far as it knows, it's just following instructions.
Finding those sounds like detective work. Does the book give strategies?
It offers some high-level approaches. They call them the R's, roughly.
Okay.
Reading your code. Slowly, carefully. Compare it to what you think it should be doing. Running experiments. Change inputs. Add print statements to see intermediate values. Tweak a line of code. See what happens.
Makes sense.
Ruminating. Just stop and think. Look at the error message, if any, the traceback, the symptoms. What kind of error is it? What could possibly cause that behavior? And sometimes retreating.
Going back.
Yeah, if you just added a bunch of code and now it's broken, go back to the last version you know worked. Then add your changes back one small piece at a time until the error shows up again. Then you know where the problem is.
That sounds like a solid plan. The book also lists some specific error names we'll likely see.
Oh, definitely. You'll see name error if you use a variable name before assigning it a value. Type error if you try an operation on incompatible types like adding a number to a string directly. Value error if the type is okay, but the value isn't appropriate for the operation, like int hello. Key error if you try to look up a key in a dictionary and it's not there. Index error for bad sequence indices.
Right.
Attribute error is common trying to use a method or attribute that doesn't exist for an object. You often see attribute error on none type, which is a big clue that a function you expected to return something useful actually returned none. And for some programs, maximum recursion depth exceeded. We'll get to recursion later.
Okay, lots to watch out for. So we have the basics. We know about errors.
Yeah.
How do we start organizing code beyond just a simple script?
Functions are the key. They're named sequences of statements that perform some specific task. You group the statements, give the group a name using the def keyword, and then you can run that whole block of code just by calling its name.
And functions can take input, right? Parameters and arguments.
Exactly. In the function definition, you list parameter names inside the parentheses. These act like local variables inside the function. When you call the function, you provide arguments, which are the actual values that get assigned to those parameters for that specific run of the function.
And those parameters, variables inside the function, they're separate from variables outside.
Yes, they are local. They only exist while the function is running. They don't interfere with variables of the same name outside the function.
So when you call a function, the program sort of jumps.
It does. The flow of execution normally goes line by line, but when Python hits a function call, it jumps to the first line inside that function definition, runs all the statements there, and when the function finishes, it jumps back to exactly where it left off in the original flow and continues.
And functions can produce results, right? Give something back.
Yep, those are called fruitful functions. They use a return statement to send a value back to the point where the function was called. Think of math functions like math.sqrt. It returns the square root value.
What if a function doesn't return anything?
Those are often called void functions. They just perform an action, maybe print something or modify something. Technically, in Python, they implicitly return the special value, none. And a key point the book makes: if a fruitful function returns a value, but you don't do anything with it, like assign it to a variable or use it in an expression, that return value is just gone, lost.
Ah, okay. You have to catch it.
Yep.
And you can combine these things, use function results as inputs to other functions.
Absolutely. That's composition. You can use any expression, including a function call that returns a value as part of a larger expression. Print him. Abs and 5, 9, 10, navs 10. That's composition right there. Building complex behavior from simpler pieces. It's fundamental.
Okay, so functions organize code. What about making decisions or doing things repeatedly?
Yeah.
Control flow.
Right. Conditional execution lets your program choose different paths based on conditions. The simplest is the if statement. You give it a Boolean expression, something that's either true or false. If it's true, the indented code block under the if runs.
And if it's false.
Then it just skips that block. You can add an else block, which runs only if the if condition was false. So you get two possible paths.
What if you need more than two choices?
Then you use elif, which is short for else if. You can have multiple elif clauses. Python checks the if condition, then each elif condition in order. The very first one that's true gets its block executed, and then the whole structure is finished. It skips any remaining elifs and the else.
Got it. And for doing things over and over, iteration.
Iteration is about repeating a block of statements. The book mentions it alongside recursion as the two main ways to get repetition. The while statement is a common tool for iteration.
How does while work?
It has a condition, just like if. As long as that condition evaluates to true, the indented block of code keeps executing. When the condition becomes false, the loop stops, and execution continues after the loop. You can also use a break statement inside a loop to jump out immediately, even if the condition is still true.
The book uses Newton's method for square roots as an example when talking about algorithms.
Yeah, an algorithm is just a well-defined step-by-step process for solving a class of problems, like a recipe, but for computation. Designing algorithms is a huge part of computer science, and Newton's method is a great example of an iterative algorithm.
Also makes that interesting point about how some things humans do easily are hard to make into algorithms.
Right, like understanding language, recognizing faces. Those are incredibly hard to pin down into the kind of precise mechanical steps a computer needs. It's a fascinating contrast.
And the other way to repeat things, recursion.
Recursion is when a function calls itself. It sounds a bit weird, but it's a really powerful and elegant way to solve certain problems specifically. Problems you can break down into smaller, self-similar versions.
How does it stop? Doesn't it just call itself forever?
It needs a base case. That's a condition within the function where it doesn't call itself again. It just returns a result directly. Without a base case, you get infinite recursion, which leads to that maximum recursion depth exceeded error we mentioned.
Visualizing that must be tricky.
The book uses stack diagrams, which are really helpful. They show how each time the function calls itself, a new frame gets added to the call stack holding its local variables. When a call hits the base case and returns, its frame is removed, and the process unwinds back up the stack.
Okay, so basics, errors, functions, control flow, repetition. Now, how do we handle collections of data, multiple values together?
That leads us to data structures. The book focuses mainly on sequences, ordered collections, and mappings. The main sequences are strings, lists, and tuples.
Ordered means the items have a specific position.
Exactly. And you access items using their position, their index, with the square bracket operator. And critically, in Python, indices start at 0, not 1.
Always got to remember that zero-based indexing.
Always. You can also get a subsequence, a slice, using dot notation with start and end indices. The len function tells you how many items are in a sequence, and looping through all the items, traversing the sequence is super common, often done with a for loop. Oh, and the in operator lets you quickly check if a value exists within the sequence.
Let's tackle strings first. Sequences of characters, we said. What's their defining property?
They are immutable. This is huge. Once you create a string object, you cannot change that specific object. If you do something that looks like changing a string, like slicing or using a method like upper, Python actually creates a brand new string object with the result. The original string is untouched.
So methods like find or count don't change the string?
Nope. Find returns the index where a substring starts, or nebis1, and count returns how many times a character appears. They just give you information about the string.
Okay, immutable strings, what about lists? They're sequences too.
Lists are sequences, but they can hold items of any type, numbers, strings, even other lists. And the key difference, lists are mutable.
Mutable meaning?
Changeable.
Exactly. You can change a list object after it's created. You can change an element at a specific index using assignment. My list equal new value.
And lists have methods for changing them. Lots of them. Append adds one item to the end. Extend adds all items from another sequence to the end. Sort modifies the list in place to put the items in order.
In place, so it changes the original list.
Yes. And importantly, the sort method itself returns none, not the sorted list. That catches people sometimes.
Could you combine lists, like add them together?
You can use the plus operator to concatenate two lists, but that creates a new list containing all the elements. The operator repeats a list, also creating a new list.
How about removing items?
Several ways. Pop removes an item at a given index and returns the removed item. The del statement can remove an item by index or even a slice, and remove removes the first occurrence of a specific value you provide.
The book also nods towards things like map, filter, reduce.
Briefly, yeah. These are functional programming patterns often used with sequences like lists to transform or select items in concise ways, but the core list operations are the main focus early on.
This mutable versus immutable distinction seems really important, especially when you talk about objects and values.
It really is. Variables in Python don't contain the objects. They refer to objects stored somewhere in memory. When you do A equals 1, 2, 3, A is a reference, like a pointer or a tag, pointing to that list object.
So what happens if you do B?
Now, B refers to the exact same list object that A refers to. This is called aliasing. Both variables are aliases for the same object. You can test this with the is operator. A is B would be true. This is different from A equals B, which checks if their values are equivalent.
And aliasing matters most for mutable things, like lists.
Hugely. Because A and B point to the same list, if you modify the list using B, say B append 4, that change is visible when you look at A, because it's the same list. A will now be 1, 2, 3, 4.
Ooh, that sounds like a way to introduce bugs if you're not careful. Unexpected side effect.
Absolutely. It's especially relevant when you pass mutable objects like lists as arguments to functions. The function receives a reference to the original list, so if the function modifies the list, making it a modifier function, it's changing the original list that was passed in.
So if you don't want that.
You need to explicitly make a copy of the list inside the function before you modify it. Slicing the whole list, like new list, original list, is a common way to make a shallow copy. Or using functions like sorted, which returns a new sorted list, leaving the original untouched.
Okay, sequences covered. What about the other main collection type? Mappings.
That's dictionaries. Think of them like real dictionaries. They map keys to values. Instead of word to definition, you have a unique key that maps to an associated value. They're unordered collections.
Unordered, so position doesn't matter, like in lists.
Nope. You access values using their specific key, not an index. You create them with curly braces and use square brackets with the key inside. Value equals mydictee.
What can you use as keys? Anything.
Keys have to be hashable. Practically speaking, that means immutable types. Numbers, strings, tuples are common keys. You cannot use mutable things like lists or other dictionaries as keys.
But the values can be anything.
Values can be whatever you want. Integers, strings, lists, other dictionaries, custom objects, anything.
Are there useful dictionary methods?
Definitely. GetKeyDefault is great. It tries to look up the key, but if it's not found, it returns the default value you provide instead of crashing with a key error. Keys, values, and items give you ways to iterate over the keys, values, or key-value pairs, respectively.
The book shows a really common use case. using dictionaries as counters, like for histograms.
Yes, it's a classic pattern. You loop through some sequence. For each item, you use it as a key in the dictionary. If the key isn't there, you add it with a value count of 1. If it is there, you just increment its current count. Super efficient way to tally things up.
What about going the other way? Finding a key if you know the value.
That's called reverse lookup. Dictionaries are optimized for key-to-value forward lookup, which is usually very fast constant time, 01 on average. Reverse lookup, value to key, is much slower because you generally have to iterate through all the values until you find the one you want. It's not what they're designed for.
Can you signal an error if the value isn't found during reverse lookup?
Yeah, the book shows how you might write a function for reverse lookup and use the raise statement to explicitly trigger an error, like a value error or a custom exception if the value isn't found.
And one more dictionary trick mentioned. Memos. For performance.
Memoization. It's a clever optimization, especially for recursive functions that tend to recalculate the same results over and over, like a simple Fibonacci function.
How does it work?
You use a dictionary, often called a memo, to store results you've already computed. Before doing a computation, you check if the result for the given input, which acts as the key, is already in the memo. If yes, you just return the stored value instantly. If not, you do the computation, store the result in the memo, and then return it. Avoids redundant work.
Clever. Okay, last collection type. Tuples.
Tuples, they're sequences, just like lists. You usually create them with commas, often surrounded by parentheses like point, 10, 20. A single element tuple needs a trailing comma, like
So like lists, but what's the catch?
The big difference, tuples are immutable, like strings. Once you create a tuple, you cannot change what's inside it.
Ah, immutable again. So you can access elements using indices and take slices.
Yes, exactly, like lists and strings for accessing elements.
But because they're immutable,
yeah.
they have an advantage we just discussed.
Right. They are hashable, which means you can use tuples as dictionary keys, unlike lists. If you need to use a compound value, like an XY coordinate, as a key, a tuple is the way to go.
The book also showed some cool Python syntax involving tuples, like tuple assignment.
Yeah, tuple unpacking. It's really convenient. You can have a sequence on the right side and multiple variables on the left. Python assigns the elements of the sequence to the variables in order, like x, y equals point. The number of variables has to match the number of elements, though.
And the asterisk operator does some special things with tuples and functions.
It does. In a function definition, args will gather any extra positional arguments passed to the function into a single tuple named args. In a function call, mytuple will scatter the elements of mytuple, so they're passed as individual positional arguments.
Also, zip was mentioned.
Zip is neat. It takes 2 or more sequences and pairs up the corresponding elements into tuples, like zipping 2 lists together element by element.
Okay, we've got the building blocks, control flow, collections. What's the next level of structure the book introduces for organizing our programs?
That takes us into object-oriented programming, or OOP, specifically defining our own types using classes. A class is like a blueprint for creating objects.
Objects being instances of the class.
Exactly. The class bundles together data, which we call attributes, and functions that operate on that data, which we call methods. You define a class using the class keyword.
And once you have the class blueprint, you create objects from it.
Right. Each object created from the class is an instance. It has its own set of attributes named pieces of data associated just with that specific object. You access them using .notation, .objectName, .attributeName. The book uses examples like a point class with X and Y attributes, or a rectangle class that might have width, height, and maybe a corner attribute, which is itself a point object.
And these objects we create, can we pass them around like numbers or strings?
Yep. Instances can be passed as arguments to functions, returned from functions, stored in lists or dictionaries. And importantly, objects are generally mutable. You can usually change their attributes after they've been created.
Ah, mutable again. Does that mean copying objects gets complicated?
It can, yes, especially if an object contains references to other mutable objects, like our rectangle containing a point. There's a difference between a shallow copy and a deep copy.
Okay, what's the difference?
A shallow copy creates a new object, but if the original object contained references to other objects, the shallow copy just copies those references. So both the original and the shallow copy end up referring to the same embedded objects.
So if you change the embedded object through the copy?
It changes in the original too, because it's the same object. A deep copy, on the other hand, creates a new object and then recursively copies everything it refers to, creating completely independent copies all the way down. Shallow copies, like using copy.copy, are often sufficient, but if you need total independence, you need a deep copy, using copy.deepcopy.
Got it. Now, methods, those are functions inside the class.
Exactly. They define the behavior of the objects of that class. You call a method on a specific instance using dot notation, myObject.coDoSomething.
And there's that special first parameter, .self.
Conventionally named self, yes. When you call myObject.doDoSomething, Python automatically passes myObject itself as the first argument to the method. Inside the method, self refers to the specific instance the method was called on, allowing you to access its attributes and other methods.
Are there other special methods besides regular ones?
Yes, methods with double underscores at the beginning and end, sometimes called dunder methods. Init is a really important one. It's the constructor. It gets called automatically right when you create a new instance, like p equals point. You use init to set up the object's initial state, usually by assigning initial values to its attributes.
What about stray?
Another key one. Stry should return a string representation of the object, something human-readable. Python's built-in print function will automatically call this method if it exists for the object you're trying to print.
Can you make standard operators like plus or work with your own objects?
You can. That's called operator overloading. You define other special methods like add for the plus operator, sub for may, eq5, and so on. This lets you define how instances of your class should behave with these standard operators.
It seems powerful to write code that can handle different types of objects. Polymorphism.
Exactly. Polymorphism is the ability for the same operation, like a function call or an operator, to work correctly on objects of different types. Sometimes you might implement this using type-based dispatch, explicitly checking the type of an argument with isInstance and doing different things, but often the goal is duck typing. If it walks like a duck and quacks like a duck, treat it like a duck. If an object has the necessary methods or attributes your function needs, the function can work with it, regardless of its specific class, like the histogram function working on strings or lists.
And the book also covers inheritance as a way to structure classes.
Inheritance is a major OOP concept. It lets you define a new class, the subclass or child class, that inherits attributes and methods from an existing class, the superclass or parent class. It models an ISA relationship.
Like a dog ISA type of animal.
Perfect example. The subclass gets all the features of the superclass for free, but it can also add its own unique features or override inherited methods to behave differently. The book uses a hand inheriting from a deck in a card game context, a hand ISA kind of collection of cards, similar to a deck but with specialized behavior.
So you have ISA inheritance and also has a.
Right. Has a is composition, where an object contains another object as an attribute. Like a rectangle has a point object representing its corner. These are two fundamental ways to relate classes. There's also a principle called the Liskov substitution principle related to inheritance.
Which says?
Basically, if S is a subclass of T, then you should be able to use an object of type S anywhere an object of type T is expected without breaking the program or causing errors. The subclass shouldn't violate the contract of the superclass.
The book wraps this up with a practical suggestion for how to actually design using objects.
Yeah, it suggests an incremental approach. Maybe start by writing plain functions. As your program develops, look for functions and data that naturally belong together. Then encapsulate that data as attributes within a new class and turn the functions that operate on that data into methods of the class. It's often not a big upfront design, but an evolution.
Okay, structures and memory covered. But programs end. How do we make data stick around? Persistence.
Persistence is all about saving data to permanent storage like a hard drive so it survives after the program stops running and can be loaded back in later. The most fundamental way is working with files, text files especially.
How do you work with a file in Python?
You use the built-in open function. You give it the file name and a mode like R for reading, W for writing, which creates the file or overwrites it, or A for appending to the end, .open, gives you back a file object.
And that object lets you read or write.
Yep. The file object has methods like read, to get the contents or parts of it, and write, to put strings into the file. And crucially, when you're finished, you must call the close method on the file object. This ensures everything you wrote is actually saved to the disk and frees up system resources.
When writing data, especially numbers, to a text file, formatting can be important.
It can. The book introduces the older style format operator, percent, for building strings with embedded values. You use format specifiers like percent for integers, percent for floats, general format, and percents for strings within your main string. Then you follow it with percent and the value, or a tuple of values, to substitute in.
Working with files means dealing with file names, directories, paths.
Right. The OS module is your friend here. It helps you interact with the operating system's file system. os.getCWB gives you the current working directory. Paths are just strings that locate files. They can be relative, starting from the current directory, or absolute, starting from the root of the file system.
How do you work with paths safely?
The os.path submodule has tools.os.path.osfile and os.path.osfile. Check if a path is a directory, or file.os.listender lists the contents of a directory. And os.path.join is really important. It combines directory and file names into a path using the correct separator, or for whatever operating system you're on. Avoid just sticking strings together with slashes.
What happens if you try to, say, open a file for reading, but it doesn't exist?
That'll cause a runtime error, typically an I/O error or file not founder. File operations are prime candidates for things that can go wrong.
But we can handle those errors.
Yes, using try and except blocks. You put the code that might fail, like open or read, inside the try block.